We're simulations. We're simulating two main regions of our microfluidic chip. Right here you see the simulations of basically a reaction chamber so that basically all of our reactants can come together and be able to deliver the appropriate dose by the end of that mixing. We're also simulating the initial bismuth uptake chamber. It's not quite done yet, but there's a schematic over there.
From 11 to 12.
So we're going to get a velocity profile for each region of each section, and we also have a mass fraction of mixing for each section as well.
We use the Fluent software package with the Gambit preprocessor to define all our geometries. Well, we chose the Fluent software package because it was available here to us, and prior work has been done using this software package, so we were able to use that as kind of a baseline for our simulations. My main area of focus was setting up the geometries for two-dimensional and three-dimensional analysis, troubleshooting software issues, and I did some work with the dissolution kinetics involving our sucrose layer and sucrose chamber geometry.
I worked on some of the longhand calculations to verify the flow velocity profile.
Mike and myself worked mainly on learning the software packages. I would say our main challenge is just learning the software packages, learning the nuances of each one, and verifying it so that we know we have physically reasonable data. Another challenge is creating the physical geometries of each channel is time-consuming. So obviously it took us a lot of time to make it, so we don't have a lot of room for error because we have a limited time to do the project. Also, we have to balance our certain computer processing capabilities with the amount of precision we want for each simulation.
We have used certain aspects of material science and engineering, such as like looking at the different viscosities, the way that the fluid flows throughout a channel, the materials that we should use.
The results from these simulations will directly impact our calculations for bismuth uptake and sucrose dissolution, and those are the most essential materials aspects of this project.
All right, we're the prototyping committee. I'm Ian, this is Tunji, this is Rob. So the original plan was that we would hopefully be prototyping an actual microfluidic channel system that has evolved greatly due to time constraints and material availability and things to primarily modeling the sucrose film itself. What we have done in the Fab Lab is that we've mixed up various concentrations of the sucrose film, or sucrose solution with water. We've made some thin films of them and characterized those thin films using the N and K and the XRD. And then we have also used the XRD to characterize the crystallinity of those films after they have crystallized over time.
Yeah, because we use the X-ray diffraction because the crystallized size will depend on dissolution rate. So we're trying to know how. So if we have different concentrations of the sucrose films, then we can know how the crystallized size affects the dissolution. So the smaller the size, the faster the diffusion rate.
We faced several challenges throughout working on the project. A lot just having to do with acquiring the necessary materials to complete the project. We've also had issues with just the equipment available to us based on the actual requirements that our project had. For instance, a major part of our project involves alpha recoil of bismuth into our sucrose film, which if we wanted to simulate that fully without actually using radioactive bismuth, we would need an ion implanter with bismuth and that we were capable of putting a sucrose film in. And on campus, either the facilities to implant bismuth aren't available, or if they are, the researchers that have ownership of them don't want us putting sucrose films inside their highly specialized pieces of machinery.
The primary software that we used was something called SRIM, which is based off of another type of program called TRIM. It's basically a program that models ion implantation. It uses the mass of the ion that you want to implant, as well as some characteristics of the substrate into which you want to implant it. In our case, it was sucrose. So we use the density of sucrose and the various different types of bonds in the sucrose, and then it models the nuclear and electrical interactions between the ion and the film to give us a sort of penetration depth and scattering energies. So as Tunji had mentioned earlier, the primary focus of the sucrose film is the kinetics involved, because a big part of our project is that we have this bismuth going into a sucrose film, and then that sucrose film is dissolving and being mixed. And all of that is completely based on kinetics. And so we have tried to characterize the sucrose film to determine thickness, as well as the crystallinity, because those two things will determine the diffusivity and how it'll dissolve into the water, which in turn will determine how efficient the overall chip will be.
Also, in designing our overall chip process, even though our plan has changed, whereas we're not actually creating a prototype, that we have laid out the design and how we would go about making a prototype, which all of that involves microprocessing steps, which also goes a long way in definitely cementing this as a materials design project.